Hi! Welcome to Coding Bootcamp 2023. It is a pleasure to be part of this event that brings together great professionals and enthusiasts of programming to learn and share knowledge about the latest trends and technologies in the market. My name is Cesar Romero. I work as a software architect at Ambev Tech in the city of Blumenau, Santa Catarina, in Brazil. I have more than 28 years of experience in system development, and in the last 10 years I have been working as a software architect. The objective of this talk is to present how to create high-quality systems. But what are high-quality systems? They are systems that are easy to maintain, extensible, testable, and consequently with less bugs. To achieve this goal, we must use good practices, design patterns and system architecture consolidated in the market, and proven efficient. This is not an easy task. We face many challenges, and as each developer can implement a task differently, the objective result can be the same, but the code quality can vary a lot, as well as the number of bugs. The quality of the systems depends on the standards and methodologies of work adopted, and my objective today is to present how to make what is right easy and what is wrong difficult. We must force developers to do the right thing without thinking too much about it. One of the ways we do this is to build a solution so that the dependencies flow the way they should. Steve Ardalis Smith. Historically, the layered architecture was adopted to separate responsibilities, but in this model, the business layer depends on the infrastructure layer. To solve this dependency, we can adopt the dependency inversion pattern, which is part of the solid principles. But just adopting this pattern does not solve all the problems, because the architecture was not level to the principle, and consequently creating unit tests is not an easy task, because any test ends up depending on external layers, mainly the database. To solve this problem, the architecture evolved, and Robert Cecil Martin presented the architecture known as clean architecture, where the business layer became the center of solutions, without depending on any other layer. In this way, the architecture and the dependency inversion pattern point to the same direction. With the reduction of coupling and the use of dependency injection, writing unit tests becomes a simpler and more pleasant task, and now we can replace external dependencies with mocks. Thus we have a controllable and consistent testing environment. A great challenge of this talk is the time. We have a lot to cover, and the time is short. I will start by showing the problems we are trying to solve, then the basic concepts of software architecture, clean architecture, design patterns, including dependency injection and unit testing with mocks. I will try to show in a clear and objective way the benefits of adopting these design patterns in the daily routine, and how to create high-quality systems by writing unit tests. The change of architecture, the use of design patterns and writing unit tests can present some challenges for those who are used to writing systems with Delphi. We will briefly talk about these challenges and how to overcome them. Then I will show a practical example of a system made in Delphi with clean architecture, dependency injection and unit tests. This way you can better understand how to apply these concepts in your daily life. In the end of this talk, you will understand how to write high-quality and easy maintenance systems with Delphi using clean architecture and design patterns also used by other modern programming languages currently. We will now see the basic concepts of the topics presented today, but let's start by understanding how I came to this specific topic. Before talking about design patterns, dependency injection, clean architecture and unit testing, we need to understand one of the most important parts of systems, which are dependencies. In a typical application, regardless of the architecture used, but thinking in old school, we have something like this. Direct dependency graph. The direct dependencies look like the flow on the left, where we have a class that references another class using a new instance, or a static call. See on the right, that at runtime it works the same way. A class making direct reference to another class. If we use the dependency inversion principle, it will look something like this. At compile time, we can choose between different implementations. This is done by using interfaces instead of direct reference to classes. And at runtime we have the same result as direct dependency. And we can use these interfaces to make the code much easier to test. Before talking about architecture, let's understand a little more about testing. When it comes to quality, there are several techniques and methodologies of testing. I will focus on the 3 types that I consider essential, and I believe that most of the other techniques are variations of unit tests, integration tests, and end-to-end tests. With the difficulty in creating and maintaining unit tests, the investment in other types of tests ends up being higher than it should be, which makes system development more costly and time-consuming. This pyramid is intentionally inverted to reinforce that investing more in end-to-end tests, integration tests, and less in unit tests is a big mistake, because besides being cheaper to write unit tests, it helps to find errors in the initial stage of development, which facilitates delivery through agile methodology. The ideal test pyramid is the one that invests more in unit tests, which are faster and cheaper to create, and less in integration and end-to-end tests. With the use of dependency inversion, creating unit tests becomes a simpler task, and TDD techniques help to improve the design and quality of the code that will produce systems with more quality. Unit tests will be your greatest allies in creating high-quality systems. Do not underestimate them. But it is important to create quality unit tests. I often find projects where unit tests are created only to give code coverage and satisfy quality metrics. But in the end, they do not deliver quality, and the code passes through unit tests successfully, but breaks in production. If this happens, you have a clear symptom that you need to review your unit tests and find out why the code did not break in the execution of the tests. One last concept related to testing that I want to present is mocks. Mocks are simulated objects that mimic the behavior of external dependencies, allowing them to be tested without interference or side effects. The use of interfaces and dependency injection in your code makes your projects testable, because in unit tests, instead of referencing concrete classes of external dependencies, you replace them with mocks. Don't worry, we'll talk more about these concepts later, and we created mocks in the example project of this presentation. Now that we know the importance of unit tests, I will talk about system architecture so that we can understand why this topic is important in the journey of high-quality systems. In the classic layered architecture, also known as N-tier, the business layer depends directly on a data layer that communicates with a database, and we have a user interface layer that depends on the business layer. As the interface must show the data, then indirectly the user interface layer also depends on the data layer, and consequently depends on the database. This is the traditional layered architecture. And these transitive dependencies mean that everything depends on the database, which makes testing very difficult, at least efficiently. In recent years, several architectural models have been proposed that aim to reduce coupling and dependencies. You must have seen some of them, such as onion architecture and hexagonal architecture, among others. The most important point is that they all have a common goal: the separation of responsibilities by reducing coupling. These oversimplified diagrams represent the main idea of each architecture. You will find variations of these diagrams on the internet, but as soon as you understand them, you will notice that they all have something in common. The business layer, now known as domain, is the center of everything and does not depend on anything else. The other layers are the ones that depend on the business domain. Now let's understand what clean architecture is exactly. Introduced in 2008 by Robert Cecil Martin, also known as Uncle Bob, its objective is to standardize and organize developed code, promote its reusability, as well as technology independence. Clean architecture is not a design pattern but rather a set of principles and best practices that aim to separate the responsibilities of different layers of software, making it easier to understand, develop, maintain, and test. Clean architecture is based on concepts such as domain-driven design, DDD, dependency inversion, and layered architecture. Some of the advantages of using clean architecture are: user interface independence. The user interface can change easily without affecting the rest of the system. Database independence. You can switch the database for another one without affecting business rules. External agent independence. Business rules are not tied to any specific framework or library. Testability. Business rules can be tested without the user interface, database, server, or any other external element. This diagram shows the layers of an application created with clean architecture. Note that the domain layer does not depend on any other layer, allowing unit tests to be created without external dependencies. External dependencies should be in the infrastructure layer, where integration tests will be performed, and in the user interface layer, functional or end-to-end tests are conducted. Notice the dashed red line between the user interface, infrastructure, and the application layer. It represents a runtime dependency, which will be resolved by dependency injection, simplifying the process of creating mocks for unit tests to avoid external dependencies. The user interface layer can be understood as the root of the application. It's where interfaces and corresponding classes are registered in the dependency injection container. This way, the entire system is implemented using interfaces instead of classes, reducing coupling, as previously shown in the inverted dependency graph. Although the diagram refers to functional tests and integration tests, these are not within the scope of this presentation. Clean architecture is based on domain-driven design, which also is not covered in this presentation. Nevertheless, we will use some elements of DDD in the example project's classes and project organization. The main benefits obtained from clean architecture, design patterns, especially dependency injection and unit testing are: improving code quality and maintainability, reducing coupling and increasing class cohesion, facilitating error detection and correction, boosting developers' confidence and productivity, improving code quality and maintainability. With these techniques, you can write cleaner, more organized, and readable code that follows the principles of single responsibility, open-closed, list-off substitution, interface segregation, and dependency inversion. This facilitates code understanding, documentation, reusability, and modification without affecting other parts of the system. It also helps you avoid code duplication, unnecessary complexity, and design flaws, reducing coupling and increasing class cohesion. Using these techniques, you can separate class responsibilities into distinct layers that communicate through interfaces or abstractions. This allows each class to have a well-defined and domain-related function without depending directly on other classes. You can also replace concrete implementations with more suitable ones or simulated objects, mocks, without altering the expected system behavior, facilitating error detection and correction. With these techniques, you can test the behavior of each unit of code in isolation, verifying if it functions as expected. You can also use mocks to simulate external dependencies of a unit of code, avoiding interference or side effects in testing. This enables quicker and more confident identification and correction of errors, ensuring system quality and reliability, boosting developers' confidence and productivity. Using these techniques, you can have more confidence in writing and modifying code, knowing that it's well-structured, organized, and tested. Teamwork becomes easier as the code follows a design pattern that enhances communication and collaboration among developers. Furthermore, delivering the system to clients becomes more agile since the code is ready to be deployed in any environment or platform. Projects in Delphi often have high coupling because the default templates with Delphi components were created before the development of the clean architecture model. This means that the system's classes are tightly linked to each other and to visual components, making it difficult to separate responsibilities, reuse code, and conduct tests. To adopt the clean architecture model, it's necessary to refactor existing code or start a project from scratch, following the rules of layer organization and communication. It's necessary to convince developers to start from scratch with a new perspective to understand the real advantages of using clean architecture. Many developers may resist the paradigm shift, thinking that the traditional model is simpler, quicker, or more familiar. It's important to demonstrate the long-term benefits of using clean architecture to developers, such as improved code quality, maintainability, and testability. Offering training and support to developers is also crucial for them to learn and apply the new techniques. Appropriate design patterns need to be selected for each situation and applied correctly. There are various types of design patterns, each with specific purposes and structures. It's essential to understand the problems each design pattern solves, their advantages and disadvantages, and how to implement them in Delphi. It's also important to avoid excessive or inappropriate use of design patterns, which could lead to unnecessary complexity or loss of code flexibility. Clear, comprehensive, and consistent unit tests need to be written. Unit tests are essential to ensure the correct functioning of code units, but they must be well written and well organized. Relevant test cases, expected inputs and outputs, success and failure conditions need to be defined. Descriptive names, explanatory comments, and logical structures should be used to enhance the readability and maintainability of tests. All possible scenarios, including exceptional cases and limits, need to be covered. Appropriate tools must be used to create mocks and perform unit tests. Mocks are simulated objects that mimic the behavior of external dependencies of a code unit, allowing it to be tested without interference or side effects. To create mocks in Delphi, specific frameworks need to be used, enabling the creation of mocks for interfaces and classes. To perform unit tests in Delphi, appropriate frameworks like DUnit or DUnitX must be utilized, enabling functional and structural testing with this native Delphi tool. Now, let's see the code. To help understanding the presented concepts, I've created a project aimed at showcasing the organization of files based on clean architecture principles. This project demonstrates the use of dependency injection to decouple external dependencies and includes unit testing utilizing mocks to simulate these external dependencies. The project will be available for download in my personal repository. The project was developed using Delphi 11 and employs the Sclite_demo database that comes with the FireDAC installation. This way, you won't need to install a separate DBMS or manually create the database. I used the Spring4D framework, which is the only external dependency you need to install. Dependency injection, collections, persistence, and mocks functionalities are all available within this framework. However, you can create your own framework or even use others. Particularly, for more complex projects, a different ORM framework for persistence and another for mocks might be more useful. The choice of Spring4D for this project is solely because it encompasses all the features I want to demonstrate, without the need for additional dependencies. If you don't have Spring4D installed yet, download it from the project repository. I used the develop branch in the example, and I suggest you do the same, as the master branch might not be compatible. I won't go through the Spring4D installation steps here, as there are several tutorials available online on how to install the library. For your convenience, I'll list the steps below. Download the Spring4D source code from the official repository. Make sure you're using the develop branch with the git branch command. Run the build.exe installer in the project directory and follow the instructions. The project is structured into a group of projects, separated according to the model proposed in clean architecture. I use Delphi packages to segregate files based on their responsibilities, and I suggest you do the same. This structure helps keep your code organized over time, and you don't need to deploy packages, .bpl files. Simply compile using the default project configuration, and all the code will be included in the final executable. However, if you prefer, you can organize the code within a single project and separate responsibilities into folders. In this case, you'll need to manage the organization manually, which could lead to more errors. On disk, the folders are organized as you can see in the image on the right side. The domain is the core of everything and should not have external dependencies. It contains only business rules and the necessary interfaces to communicate with other external classes that will only be known at runtime, through dependency injection. In this project you'll find entities, aggregates, domain services, exceptions, interfaces, domain events. For file organization, I don't follow strict rules. I've worked on projects where I had to create folders for just one file, but that's excessive and counterproductive. For me, the most important aspect is that you can look at this structure and understand the project without the need to navigate through multiple folders. The common folder contains service interfaces used by the services. The orders folder groups all classes related to orders. Here, you'll find entities, aggregates, services, specific order repository interfaces, and exceptions. The products folder is self-explanatory. It clearly indicates that the category class pertains to product categories and nothing else. This embodies the meaning of bounded context in DDD. You should keep all related classes together. I believe you can now guess the purpose of the classes in the shippers folder. Just like in the previous folders, we're grouping all classes related to shipments here. The other classes can remain in the root directory. There's no need to create folders for individual files. The names are self-explanatory and clear, as per the clean code principles. Entities are simple, known as POTO, plain old Delphi objects. The only peculiar aspect is the mapping attributes for database fields. These attributes are required due to a feature of Spring, persistence. However, this should not be the case. Mapping database fields causes the business layer to be aware of the persistence layer, which violates the single responsibility principle, the first principle in Solid. Ideally, mapping should reside in the infrastructure layer and can be implemented using a Fluent mapping library to simplify this step. The class TOrderAggregate is responsible for orders, and an order only exists if it has items. It also doesn't make sense to have items without an order. Given that they don't exist independently, they become strong candidates for being an aggregate according to DDD. Browsing through the code of the createOrder method, you'll notice that it verifies the validity of relationships before creating the order. If any IDs are incorrect, an exception will be thrown. After creating the order, certain date fields are filled using a date and time service. This is crucial for system integrity, especially in large companies where there's a timeline of orders, and stages might be processed in different instances with varying time zones or even unsynchronized clocks. Additionally, for consistency in unit tests, control over date and time fields is necessary. Time zones affect these fields, and it's common for pipelines to break in unit tests due to differences in time zones between the build machine and the developer's machine. Domain services are classes that orchestrate operations and flows between different domains. Their purpose is to implement a business flow. The class TShipperService is responsible for triggering the shipment of an order. It depends on two different domains, order and shipper. Additionally, it needs to update the shipping date field in the order. Hence, an instance of the datetime service is also required. After verifying the shipper and updating the order, a notification needs to be sent to the shipper. This entire flow should be an idempotent operation, which is why there's a need to create a specific service for it. The implementation in this example is straightforward. The key here is to grasp this important DDD concept. The other classes in the domain package are similar to these, so we can move forward. In the infrastructure layer, we have the implementation of interfaces used in the domain, external services like databases, configuration files, and email sending services. Each implementation is specific to a single functionality. Date-time service is the provider of date and time. Email notification service is responsible for sending emails. It's not yet implemented in this project, and it's only present to represent the concept of domain events in tshipper service. Database repository implements the iRepository T interface, responsible for data persistence, and is an implementation of the repository design pattern. I've implemented it using generics, where T represents the entity class to be persisted. The methods are straightforward and clear in their purpose, with names designed to eliminate ambiguity. The only method I'd like to discuss is the whereQuery method, which takes a specification argument. It's a direct mapping of the iCriterion class from Spring, persistence. In the context of the repository design pattern, a criterion can be interpreted as an implementation of the specification pattern. The specification pattern helps keep the repository simple and clean, avoiding the need to create specific repositories for each entity whenever a new query with a different where condition is required. Still, there are cases where custom repositories for a few specific classes are necessary. Hence, I also implemented the TOrderDetail repository. Its sole purpose is to serve as an example that customizing some repositories is possible and valid. It can be for implementing complex and specific entity rules or to avoid code repetition dry. In this example, it doesn't add much to the repository and could be implemented with just one line of code using the generic repository. The where condition is implemented using the record prop from Spring Persistence. With the help of implicitly implemented operators, it returns a valid instance of iCriterion, which can be passed as the desired query specification. I prefer using this approach to avoid typing strings, especially here, as the string should correspond to the field name in the database, not the property name. You must have already realized that this would lead to various bugs during development. So, aside from serving as syntax sugar, this approach also helps prevent bugs. The other classes are not particularly special. They merely serve their purpose of isolating external dependencies from the domain. The application project is your ultimate goal, where everything is interconnected. The project is quite simple and isn't meant to be a complete functional system like an API or a data snap application server. However, I believe it can serve as inspiration, especially for projects like these. For projects involving user interfaces, a few more steps are required. You need to implement integration with forms and components using a pattern like MVC or MVVM, which aren't within the scope of this presentation's objectives. The project file performs two tasks. It calls the configure services method of the tstartup class, which is responsible for project configuration, loading settings from files, Windows registry, credentials, certificates, which are not necessary for this project, and the registration of interfaces along with their corresponding classes, factories, or delegates. With the registration of all necessary services, the container can create dependencies and inject them into constructors at runtime. This reduces coupling between classes, enhancing code maintainability and evolution without the need to rewrite everything from scratch. We don't have time to discuss each of these classes, but what's important is for you to grasp that every time we need an instance of iDateTime service, the container will provide us with the instance implemented by the registered tDateTime service class, just like all the other classes. The TOrderAggregate class depends on several other classes, all registered in the container. Consider this example on the marked line. When the container resolves iOrderAggregate, it will create instances corresponding to all the classes declared in the TOrderAggregate constructor, along with the dependencies of these classes, and inject them into the corresponding constructors. Besides offering flexibility in the architecture of the code, this approach also keeps the code clean, eliminating the need to manually create instances and pass them into constructors. Even worse, it avoids creating dependencies directly where they are used, which would increase coupling and the dependency between classes. We're nearing the end of the presentation, and now let's discuss unit testing and understand how everything we've done so far will help us create better tests and, consequently, higher quality systems. For the example project, I've created unit tests for the tShipper service and tOrderAggregate classes. However, in this presentation, I'll focus on the tShipper service tests, as they are easier to understand. The tOrderAggregate tests will be left as homework in case you'd like to explore tests for classes with more dependencies and potentially more complexity. Before we delve into the code, I need to make an important note. To create a mock for an interface, it's necessary for the interface to have generated RTI. To achieve this, you need to include the directive $m+ before the interface. Now, let's understand how to create and set up mocks. All dependencies are declared using mock, interface, created, and configured in the setup method of the test. This setup is quite straightforward. We create mocks for the dependencies of the tShipper service class, which will be our service under test SUT. It's created in the last lines of the setup, receiving its dependencies as constructor arguments. In these three highlighted lines, we create a mock instance of iDateTime service and set it up to return the fDateTime when the today method is called. In summary, instead of executing the code implemented in the concrete class, for the purpose of unit testing, we use a substitute instance where we can control its behavior during testing. This ensures consistent behavior across all executions, regardless of the environment, whether it's on a developer's computer or a build server. The shipper repository also needs configuration, but I've left that to be set up in the test methods. This is because we'll configure it differently for each method. The name of the test method should describe what the test does. There are various conventions, and you can adopt the one that suits your needs best. I've used the same approach as I do in my daily work. The name of this method should be interpreted as when the shipOrder method is called. It should update the shipDate field of the corresponding order and trigger a notification. Unit tests start with setup. Here, we configure the getById method of shipper repository to return the instance we created in the setup. We also create an instance of the order entity to pass as an argument when calling the shipOrder method of the tShipper service class. At line 77, the method is invoked and should execute all lines of the method except line 52, which is the exception in case fShipperRepository.getById doesn't return the configured entity. At line 80, we check if the update method of the repository was called once. If it wasn't called or was called more times, the test will fail. Next, we use assert to verify if the shipping date of the order was updated with the date we configured in the mock of iDateTime service. If the value is different, the test will fail. In the next two lines, we verify if the send method of iNotification service was called with an argument of type tMessage containing the instances of shipper and order used in the previous steps. In this case, we also ensure that the method is called only once with the argument times once. High-quality unit tests should cover as much of the code as possible. This means that if a method contains if, else, loops, case statements, or exceptions, we should create test cases for each of these possible flows. Now, let's closely examine the method being tested to ensure we're truly providing comprehensive coverage for all the flows. In the previous tests, we ensured good coverage and verified that the update methods of the repository and the send method in the notification service are each called once. However, one flow is still missing. What happens at runtime if the shipper is not found? Line 52 raises an exception and disrupts the normal flow of the method. We need to cover this case as well, ensuring that if a shipper is not found, the correct exception is executed as expected. Let's start with the method name, which declares that it should raise an exception if the shipper is not found. The repository setup is configured to return nil when the getById method is called, which is what will happen in production if the corresponding record doesn't exist in the database. Assert.willRaise executes the code provided in the anonymous method and checks if the eShipper exception is raised. If not, the test will fail, and the message passed in the last argument will be printed along with the test failure error. In the following lines, we validate that the update method of the repository and the send method of the notification service were not called at all, and that the shipDate field was not updated. And with that, we conclude the material I've prepared for you today. I hope these examples and explanations have been clear enough, and that I've managed to at least spark your interest in clean architecture, unit testing, mocking, domain-driven design, and design patterns. In this presentation, we have seen how to use design patterns and unit testing to create quality systems with Delphi. We have learned the basic concepts of clean architecture, dependency injection, mocks, and unit testing. We have highlighted the benefits of improving code quality, maintainability, error detection and correction, as well as developer confidence and productivity. We have also discussed the challenges of refactoring existing code, convincing developers to embrace a new paradigm, choosing and applying suitable design patterns for various needs, writing clear, comprehensive, and consistent unit tests, and using appropriate tools to create mocks and conduct unit tests. Finally, we have witnessed a practical example of a Delphi system implementing clean architecture, dependency injection, and unit testing. Unfortunately, we didn't have time for a presentation on a larger and complete system. The aim was to provide guidance for those interested in these topics and to show that further exploration is necessary to achieve success as a high-performance developer or even as a software architect if that is your goal. I would like to express my gratitude to all of you for your attention and interest in this presentation. I understand that time is a precious resource, and I greatly appreciate you dedicating part of it to learn about these subjects. I hope you have enjoyed and gained new insights today. If you have any questions or curiosities about the presentation topic, please feel free to reach out to me directly. If you have opinions or experiences regarding the use of design patterns or unit testing with Delphi, please share them with us. I would be delighted to hear and address your inquiries and contributions. To conclude this presentation, I would like to leave you with a motivating and inspiring message. The use of design patterns and unit testing with Delphi is more than just a technique or a tool. It is a way of thinking and creating systems that are efficient, reliable, and sustainable. It is a means of expressing your creativity, skill, and passion for programming. As Uncle Bob, one of the creators of the clean architecture concept, once said, "The only way to go fast is to go well." I hope this presentation has inspired you to do things well and efficiently in your Delphi projects. Thank you very much for your attention, and until next time.